All right, Ben, floor is yours.
All right, everybody. Well, it's ready to start. So, welcome to Generative Adversarial Networks Part 2. I hope everyone had a good Thanksgiving. Welcome back to reality. Happy Monday morning. We're going to do a quick recap of what we talked about last time, and then we're going to dig into what the actual optimization and stabilization issues are with GANs, and then if we have some extra time, we'll roll back to the end of the last lecture and talk about some GAN architectures that are interesting. Anyways, recap. So far, we talked about what a GAN is and kind of the basic theoretical framework of the two-person game, and generally about what kind of things they can do. So GANs are generative networks. You can use them to create data, and you can use it to create data wholesale or conditionally or in many different variations that we'll talk about. So what a GAN is, it trains a generator to produce samples from the target distribution, and it has a discriminator network, which is this other adversary, which helps to guide the discriminator and tells it what to do. The generator or the discriminator are adversaries, they're trained against each other, and this fight between them is what makes the GAN actually work. So theoretically, what they are doing is calculating the divergence between the generated and target distributions. They're calculating a Jensen-Shannon divergence. We mentioned briefly what that is, but basically you have a distribution trying to create a distribution that you're producing. Your discriminator is calculating what the divergence between the two of those things are, and then your generator is trying to minimize the divergence, and overall that means this distribution matches that distribution based on some metric that is this divergence that we're calculating with the generator or with the discriminator. If you want to make one yourself, you make your generator network. Your generator network needs to take random data, some latent distribution, some sort of noise, and make it into an image or into audio or whatever. You've got this one network that goes from latent to your image to your audio. You've got another network with your discriminator, which goes from your audio or your image or whatever it is, and outputs a number. The scalar is that real or is that fake? So you take random data, that's your Z, that comes from the prior, and you take real data, which is X, which comes from your images, your audio, whatever it is. And your discriminator tells the difference between generated data and the real data. Generated data is you take Z and you put it into your generator. Real data is just your X. You tell the difference between those two things, and your discriminator learns to tell the difference, and your generator tries to do the opposite, which is to confuse it. So when people are trying to describe what a generator is, confusion is one of the words they like to use, but if your generator confuses your discriminator, then your generator is doing well. By confusion, we mean we've got this generated data and we've got real data, and your discriminator can't tell the difference between the two of them. It's confused. Therefore, your generated and real data are really similar. If your discriminator can't tell the difference between real and fake data, your discriminator is confused, your generator is producing good data, that's mission accomplished. In terms of what you can do, it's more than just generating data. You can use GANs for different types of clustering, for semi-supervised learning, representation learning. You can use it for translation. You can use it for audio. You can use it for images. You can really use it for any sort of framework you're dealing with. So it's a powerful tool, lots of potential. The real issues with GANs are actually getting them to work, getting them to train correctly, getting them to do what they're theoretically supposed to do, because in practice, you'll end up getting a lot of junk if you don't do it correctly. So we're going to talk today about some of the pragmatic issues and how you actually get it to work better. So, to start with, one second. Oh, pardon me. So, a lot of people had questions last week about why there's no optimal discriminator and why you have to do them back and forth. Why can't you just do one at the time? Why do you have to do them together? So to try to kind of understand that, I think a good example is just rock, paper, scissors. So let's say there are two players that are adversaries and they're playing rock, paper, scissors. And I, as the first player, I have a random strategy, and the random strategy is this one right here. It's 36% rock, 32% paper, 32% scissors. If that's my strategy, what is your best strategy for playing against it? What is the optimal play style? If you could pick your likelihood of rock, paper, and scissors playing against my strategy, what what probabilities would you pick to have the best likelihood of winning? This is actually a question, not a not a rhetorical one. So someone's playing with 36% rock, 32 paper, 32 scissors. What is your best strategy to play against that?
So it's like 36 paper, 32 rock, and 32 scissors, right?
Okay, so if you did that, what would your likelihood be of winning? And I think chat just got it. And that's what's interesting about it. So congrats to Nikki Nocerino. Apologize if I pronounce that wrong, but yeah. So if 36% rock, if you always put paper, if your response is 100% paper, then you've got a 36% chance of winning. You've got a 32% chance of drawing and a 32% chance uh, of losing. So 36% win, 32 draw, 32 lose. That is actually the best you can do. So someone is very, very close to third, third, third. Your best likelihood is 100% paper in that situation, which takes a second. It seems awkward that why would you do 100, but it actually is. If you were to do 36% paper, then your likelihood of paper versus rock would be 36 times 36. And if you actually worked out the likelihood of all the different possibilities, the highest is actually to always, always, always do paper in that situation. So to change the situation a little bit, let's say it's exactly a third rock, a third paper, a third scissors. What is your best strategy in that situation? Can anyone guess what the best strategy is to play against someone who's completely random? It's kind of a trick question. Well, it's everyone. But the right answer is every single strategy you play is the optimal strategy. It's everything you do, no matter what you do, you'll have a 30% chance of winning, or 33% chance of winning. So in this situation, what you need to understand is that if someone is slightly more likely to do rock, whatever thing they're slightly more likely to do, your best option is to argmax whatever it is that they're weakest against. If they were 36% papers, you would go 100% rock, and that would be your best strategy. If they were 36% paper, you would go 100% scissors, and that would be your best strategy. However, if someone is exactly a third, a third, a third, then every single thing you do has a 30% chance of winning. So everything is technically the optimal strategy. And when you look at it that way, you see how when things are slightly off, there's a very strong the best thing for you to do is go all the way in one direction. And the only time when you don't go all the way in one direction is if they're 30, 30, 30. So basically, if it's anything but 30, but a third each, your strategy is going to be 100% into one thing or another. And the only time when your optimal strategy isn't 100% into one thing is when it's completely flat, completely random. And in that situation, all of your strategies are optimal no matter what you do, no matter what your ratios are. So that's just a basic example because you guys know what rock, paper, scissors is. If we look at that in how that applies to generative networks, we can see a very similar situation. So let's say that our domain is just generating heads and tails. We've got a network, it generates zeros and ones at some ratio, and our real data is zeros and ones at some ratio. So we've got our real data, we've got our generator, our discriminator says that zeros get this value and ones get this value, and that makes our generator do more of this or more of that. So let's say we just, it's very simple 0, 1 discriminator generator situation. Let's say we have that situation and our discriminator outputs is 51 heads and 49 tails. If we kept that discriminator completely static and trained our generator all the way with that discriminator, what do you think the optimal generator for that discriminator would output? And hopefully the rock, paper, scissors example was a good right. If the discriminator is slightly higher on heads than it is on tails, and then you just trained a generator against that, the generator would eventually do 100% heads. Because if heads is slightly higher than tails, then your best strategy is to be 100% heads. And the flip side, if your discriminator was 51 to heads and 49 to tails, then the optimal generator would put everything into tails. Because tails is 51, heads is 49. So exactly like rock, paper, scissors, it would go all the way into tails. And then let's say our discriminator gave a 50 for tails and a 50 for heads, then that would be the situation where there is no optimal discriminator, or they're all optimal discriminators, depending on which way you look at it. But if it's 50 heads and 50 tails, then any single thing the generator outputs has the same, is going to give you the same value, it's going to give you the same results, just like rock, paper, scissors. So it's a little abstract, but what does that mean? Your discriminator tells you which way you should move. It doesn't tell you your end result. So the feedback from the discriminator is, oh, this situation here, 51 tails and 49 heads, that means you should move towards tails. And 50 tails and 50 heads means you don't need to do anything, you should stay where you are. The discriminator isn't telling you where you should end up. The discriminator is telling you move this way or move that way. So if there's a static discriminator, if you hold the discriminator steady and you optimize a generator against that, you're going to get junk data, because your optimal generator is against a static discriminator is either going to be 100% heads or 100% tails. And that's not what you're looking for. You're looking for 60-40, whatever it's supposed to be. And the only way that can work is if the generator and the discriminator are trained together. If they're trained at the same time, if you don't have enough heads, then your discriminator will put heads above tails, which will make your generator start producing more heads. And as your generator starts doing that, once it gets to a point where it hits more heads than the other, then the discriminator will be negative there, which will make it go less. And the discriminator will tell it to go more and less and to stop until it gets to the point where it is. But what that means is your discriminator you should think of as like the velocity, not the position you want it to be at. So the discriminator is only giving you important information based on where the generator is right now. So last time we talked about, and to compare this to what we did last time we determined here is the optimal discriminator for every single generated point, and then we analytically optimized both of them and said, oh great, we're minimizing the Jensen-Shannon divergence. And that is what you're doing when you do the two of them and get the joint optimization. But if you're just going, let me take a discriminator and find what's the optimal generator, if you're just doing the optimal generator, you're ending up with basically an argmax. And that's not what you want. It's just going to give you the image that is the most likely. It won't do some of this and some of that. So really, that's one of the core reasons why GANs are hard and they're hard to train, because you can't just do one or the other. They have to go back and forth. And this leads to a lot of different failures of GANs. So some of the common failures that you'll see, one of them is called mode collapse. When you're actually training your GAN, by the way, can you see these? Does the video work in the share screen, hopefully?
Yeah.
Yeah, okay. Good. Opened a new tab, so I wasn't sure. So this is what mode collapse looks like. So I'm training images, I'm training on MNIST, everyone knows what MNIST looks like. And you start to look at what it's producing, and it's like, I'm training it on 0 through 9. And what I'm getting is a bunch of 1s. And I'm getting a lot of different versions of 1s. And as I train the network, this is during training. So as I train the network, it starts to actually lose variety. And it's just starting to produce here a bunch of different versions of the number 1. I gave it 10 different digits to produce, and it only produced one of them. It's kind of focusing in on this one little area and not doing everything. In GANs, that's called mode collapse. And that's obviously not a good thing. That's something you want to avoid. But if you are not training correctly, do I have to get out of this to... sorry, I need to get out of that to get back to it. Okay, and I need to reopen. Sorry, 1 second. Full screen. Here we go. So when you're training GANs, one of the helpful things to do is just trying to take pictures of the images and see what you're generating and try to diagnose issues that way, because they're very hard to diagnose problems. And some problems you can put into a nutshell. Some problems are very hard to describe. So you can end up in cycles where nothing ever converges. You end up with random stuff coming out, all caused by certain caused by one issue we're going to talk about later, plus the needing to go back and forth that we just talked about. And there are all types of issues you can end up with when you're training if you're not doing it with good networks, not implementing it correctly, and especially if there's just not a balance between the two of them. So it requires a balance between players. And there is this stationary point, but whether you actually get there or not depends on a lot of other factors. It's not single player where everything optimizes and optimizing works. When you're optimizing two things against each other, you might not have something working. Simultaneous updates are very important in this issue, as we just talked about, and you can visualize it both if, let's say, the discriminator is not trained well enough. If the discriminator's not fully trained, then you're going in the wrong direction. You're not getting good data. If your discriminator is trained too much, this is a network with a sigmoid, and you will actually overtrain it and not get reasonable data. And the way that you can affect the balance between the two of these things, many different factors go into: is your generator training fast enough? Is your discriminator training fast enough? The way you can affect that depends on what the optimizer is. If you've got something like Atom versus SGD, they're going to train at different rates. If you have a higher learning rate or a different learning rate for your generator and for your discriminator, you can change the balance between the two of them. If you have different architectures and numbers of parameters, you can change the balance between the two of them. If one network is very, very deep with a lot of parameters, it might not train as quickly as a really small, simple network. If you have regularization in one network or something else that's making it harder for one network to learn than the other network, If you increase regularization on your discriminator, in effect, your discriminator is going to train a little bit slower than it was training earlier, and that can affect the balance of your GAN. Another way you can directly affect the balance is you can train more often or less often for the other. So let's say you were to do, I'm going to do 1 step of my generator and then 5 steps of the discriminator. That would keep my discriminator ahead of my generator while still doing them at the same time. So there are all types of things that affect how fast one versus the other happens. And you don't really worry about those when you're doing a single network, because if you increase the number of parameters or change the learning rate, you might learn slower or faster, but that's not going to affect whether something works. Versus in a GAN, if one thing's training too much faster or slower than the other guy, you actually don't get results, or you get junk results. What this actually looks like in practice, if things are not too, I might actually skip that video for time's sake, but you can envision that in rock, paper, scissors. So let's say someone was a little bit off. Let's say my strategy was that 36% paper. If I then let you optimize all the way, actually the example here is, let's say I'm slightly more likely to do rock, then player B, if they optimize it all the way, their best strategy should be 100% paper. They would go 100% paper to beat my rock. And if they did that, then A should go 100% scissors. And if A went 100% scissors, B should go 100% rock. And you can imagine that cycle, and that cycle would never end. If 2 players take turns picking their rock, paper, scissors strategy and picking the one that's the best one against what the other person's playing right now, then they will go through a rotation and they will never end up stopping at the best strategy for each of them. Because the best strategy to beat you on this turn would lose to your choice on the next turn, et cetera, et cetera. And that's really what what it looks like in practice. So mathematically, as you were talking, the actual calculation for your expected losses based on yours and what the other person has, and I think this equation should make sense, which is the likelihood that the probability that A is going to let's see this win, the probability that A is going to win is the probability that A is doing rock times the probability that B is doing scissors plus A doing paper and B doing rock and A doing scissors and B doing paper. And if you add up those 3 likelihoods of winning, that is your likelihood of winning. But if we were to actually try to run this, what I did here is gradient descent, rock, paper, scissors. So I've got 2 players, one guy's rock, one guy's A, one guy's B. And if you actually do the training, you end up with an oscillation like this. And I probably should have done it a little slower, but you see right here, B is playing rock and A is playing paper. So that makes B go over to go scissors to try to beat the paper, but then the other one becomes rock. And they just take turns, they do gradient descent, and maybe they don't eventually always go to 100%, but you can end up with oscillations like that in GANs. They're just easier to understand if you're looking at rock, paper, scissors, for example. So if you can understand why 2 people playing rock, paper, scissors, we know the ideal is for them each to go 33% and 33%, and that's the best for both of them, and that will get both of them the best loss that they can possibly get. But if you do gradient descent of the 2 people against each other, you will never get to that point unless you start adding in other things. There is a stationary point, but there's no point towards the stationary point. Because if you are exactly at that 30, 33, 33, 33, you're doing well. But if you're slightly off in one direction, then that pushes the entire system into another place. The system starts oscillating more if you're just slightly off from the difference. And that's like balancing a pencil you're talking about, where that perfectly balanced pencil is your 33% completely even. That's what you should be doing in rock, paper, scissors. But if your strategy is slightly off in one way or the other way, then the other person's strategy will be 100% off, which means you need to be 100% off, and that's what causes these oscillations. So, how do we avoid this? How do we get the best GAN? There's no silver bullet. There are a lot of strategies which make things better and worse. There are a couple strategies which are personally the best and the ones you should really be using. But there's a kind of long history of different techniques. So we're going to talk about some of the different techniques people have used and focus in on some of the best ideas, but some of them might be historical, some might just help you get an idea of what kind of research is happening. But really what these techniques go into, here's a set of what we'll be looking at. We won't be diving too deep into each of them. Bold are the ones that I would like you to know and try in your own code because they work the best. But this will give you a sense of where the issues are coming from and what things people have done to try to make the optimization issues better. Should put it back in full screen. So one of the earlier ideas that's actually very interesting is called unrolled generative adversarial networks. Unrolling has to do with kind of game theoretic. It's the idea that you don't want to play what is the best strategy to beat my opponent's current best strategy. You want to play what's the strategy that will beat whatever my opponent comes up with after I do my new strategy. So I'm not trying to beat what's your current, you're playing rock a little more, therefore I need to play a bunch of paper. I go, oh, if I start playing a bunch of paper, then he's going to play scissors, and then I'm going to lose 100% of the time. I need to play the best strategy regardless of what the other person does. So in math, though, how do we actually do that? And the way we can do that is project out the gradient descent steps and optimize against that. So instead of optimizing against the current discriminator, you optimize against where the discriminator would be if it got a couple chances to update against you. So it's not, and this is the reward. It's basically instead of what the discriminator is right now, let's take the current discriminator steps, and those are going to do gradient descent. So you can actually play out 5-10 steps of gradient descent of the discriminator and train the generator against where the discriminator will be based on where you've changed. And that way the changes the discriminator will do actually guide your generator to a point that cannot be beaten regardless of what's going to happen. And this strategy is supposed to work in basic game theory and basic rock paper scissors whatever, but it actually works in this generator discriminator framework. So that's the definition. The implementation is a bit trickier because basically what it involves is you need to do several updates of the discriminator in memory and then backpropagate through those to find what would have been the best option. And here's kind of the diagram of it, which is you do steps of SGD to update the discriminator, and then you actually unroll and backprop through all of those to get your better generator gradients. Result-wise, we actually see that this fixes things like mode collapse. So I believe the top column is training some steps and what happens, and they're trying to get to this simple circle. And the bottom one is mode collapse. So mode collapse, if you were trying to reproduce these 8 points, would just pick a point, and it would put all the data at that one point and not diversify. So in some simple experiments, you will see that using the UGAN avoids mode collapse and makes things look prettier and makes things actually train pretty well. relatively effective, kind of tricky to optimize, and there are better methods. But what you should take away from the UGAN is this idea of um, trying to find the best solution regardless of what the other guy does, not just the current best solution. And what it's doing in practice is actually doing some regularization of, sorry, it's not letting me scroll. Oh, there we go. It's actually going to be a form of regularization. And we'll dig more into what that regularization looks like when we see other GAN techniques that are going to do something similar. So another paper that was pretty interesting is just called Gradient Descent GAN Optimization is Locally Stable. And what this does is it just tries to minimize the gradient of the discriminator. So one way to think about that is if your discriminator has a very large gradient, then that means if your discriminator is taking a step, then your discriminator is going to make a large change, is going to do a lot better on that step. It's pretty simple. Think about you're doing gradient descent. If you're currently doing gradient descent at this point, and the gradient at this point is really, really big, that means that I think, at least from first order approximation, whatever, that if I do a small move, I'm going to make a big, big change in my outputs. And if the gradient's low, then that means no matter what I do, I'm not going to be able to make any improvement. So when you're training your generator, if your generator tries to do really well, but it also tries to minimize the gradient of the discriminator, then that means the discriminator can't improve itself. The discriminator has no way to do better. It's not exactly what we just said before on the UGAN paper, but it's a similar idea, which is my GAN is not just trying to do the best right now. If my GAN does my best right now, but also the discriminator doesn't have much of a gradient, then that means the discriminator is not going to come back and bite me on the next iteration. So we're minimizing that gradient of the discriminator, meaning I'm doing well, but there's no way to mess that up really easily. We see here, so that's gradient descent GAN is locally stable. Simple idea, minimize the gradient. If the discriminator has nowhere to go, then the discriminator is going to, then you're probably doing better. Another similar idea, how to train your dragon. This is actually a CMU paper. It's minimizing the norm of the gradient. Similar idea, slightly different smoothing and how it does the smoothing. But what we're looking for is if the discriminator has a low gradient, then that means things are pretty stable, they're converging, the discriminator is not moving wildly, versus if you have a generator and the generator is doing really well right now, but the discriminator's got a high gradient, then that means things are going to keep moving, they're going to keep going, they're going to keep oscillating, you might not get to where you want to be. And another similar idea, which is called the numerics of GANs, actually very, very similar, but we're still looking at minimizing the gradients of the loss. So if we want to, and in the numerics of GANs, we're actually, each player is minimizing the norm of the gradient with respect to the other player. So it's kind of like what we said in the last slide, but in the last two slides actually, but going kind of both ways. So when your discriminator updates, your discriminator tries to do really well by its objective, but also have this regularization that says, oh, and my generator can't fix it really easily. And your discriminators and your generator is also saying, I want to do as well as I can for the generator, but my discriminator should have a low gradient. And if each of the players is trying to minimize the gradient that the other person has, it means I'm trying to do something that's not risky, if that makes sense. If you're playing a game and you take the best option that also minimizes the other person's gradient, that means there's no good response to my actions. If you want to think about it really adversarially metaphor, I guess. But the adversarial metaphor is the other guy doesn't have any options, and if the other guy doesn't have any options, then you know you made a good choice. Versus if you've got a really good value, but the other guy's got a good gradient, that might mean you're doing well now, but the other person's going to optimize. That's going to change everything, and you might be doing terribly next time. So numerics of GANs, also kind of similar, but going in both directions. And consensus optimization is a terminology that was brought in with numerics of GANs. And the reason numerics of GANs is interesting is it's this consensus idea of trying to de-escalate. So the generator tries to do as well as it can while keeping the gradients low and not causing a lot of oscillations. The discriminator tries to do as well as it can while not causing as much oscillations. So it's kind of mutual de-escalation. There is the goal, as in regular generators, of generator does the best it can, discriminator does the best it can, but hey, if we could agree to not fight and move around so much, that's the right way to go. So we got this extra regularization thing, which is de-escalation, and it means let's go towards saddle points, let's go towards minima, let's just kind of settle down, find something small, and that little regularization parameter pushes you and stops those oscillations. So there's this lambda here in the equation, and that is a user-defined 10%, whatever you want it to be, and just that little bit of push is trying to make things stop oscillating and find a safer point. So visually speaking, what does the numerics of GANs do? So you've got first this non-conservative field they're labeled. They see this is what the GAN might look like, where your generator might be going. And you can see these equilibria, which are points where there are no arrows, but we see that they're not stable. Because if you were to follow the arrows around in a circle, you would loop around and around, but you would never get to that equilibria point. So here on this, you see those equilibria. Those are where you would want to be if your generator and discriminator were optimal, but you get there by following arrows, and you might not ever get there. We then come up with this conservative field. This conservative field is pointing towards all the saddle points in the equilibria. Why is it doing that? That's because that is the L2 of the gradient. So basically, if we're going down and going in the direction of decreasing gradient, then that is a field which actually points towards the equilibrium points. However, this field also points towards the saddle points. So we've got this field here on the left. This field is not leading you to where you want to go, but it does have equilibria in it. It does have these minima, and it also has saddle points, but you want to get to the minima. And then you've got this conservative field that is pointing towards equilibria and pointing towards saddle points. And then when we combine those two things together, we've got this funky looking thing over here. And this funky looking thing over here, you see these spirals. If you compare, if you pick one circular thing over here on the left and compare it to a spiral thing on the right, you see how you just add a little touch of this conservative field, and the arrows are spiraling inwards instead of just circles that are not actually going inwards. Interesting paper, numerics of GANs, works really well. Hard to modify. There are other better methods, but kind of a brilliant and interesting idea of how to de-escalate and get these things to hit the points where you want it to be. Another interesting set of GAN techniques that people have tried. Improved techniques for training GANs is a pretty big paper with a couple of interesting ideas. And some of them might just sound like hacks, but you can actually get major improvements to your results by this. Yeah, so as Bishop was saying, they also spiral to saddle points. So the idea is the conservative field points to equilibria and saddle points, but you're just doing a touch of it, and you're just adding a little bit of it to the non-conservative field. So it does kind of point towards saddle points, but they're still saddle points, and you hope that they go away. So the saddle points are still unstable. They still exist because they're saddle points, but basically the hope is that combining these two things will not just get you to the saddles. You will end up in the equilibria, and the saddles are still kind of there but unstable, and the equilibria are there but stable. And yeah, so the hope is you would fall out of a saddle. If you were in this saddle, like this upper right saddle point, you could end up there, but if you were there, you kind of fall slightly to the bottom right. You can get out of that saddle point. Versus if you're at these equilibria points, it's really spiraling into that equilibrium point, and that's where it wants to be. So some of these interesting techniques. Feature matching. Feature matching is the idea that generated images and real images should have similar statistics. So instead of a discriminator that just outputs one piece of data, just a scalar value, you could have a discriminator that produces multidimensional data. And then you're trying to minimize the L2 or trying to minimize the statistics between these two different data sets. So instead of just a single discriminator output, you can have you can have a vector of outputs, and you're trying to match the vectors of discriminated and generate of real data going through the discriminator and generated data going through the discriminator. It gives it slightly wider outputs, and that can cause a little bit of stability, a little less oscillation. The idea of mini-batch discrimination is that you can have a discriminator that takes in multiple data points instead of just one at a time. So if you can look at multiple inputs, you can have a better way to tell if they are generated or fake. So if you're just looking at one point at a time, you might not know if it's generated or if it's real, or you might not be very strongly able to differentiate those two. But if you're looking at many, many samples of the GAN and many samples of the real data, you can clearly say, oh, these are the GANs and these are the real data. So modifying your discriminator to take in multiple pieces of data at the same time, your generator is still just outputting one thing at a time. But if your discriminator looks at 2 or 3 real points and 2 or 3 generated points, and then gives you an output about which one's real, which one's fake, and doing the categorization, it could be a much stronger discriminator. Another interesting idea is just historical averaging. It's kind of a big word for a simple idea, but basically trying to directly minimize oscillations. Oscillations are when something moves and moves a lot. So we can do historical averaging, which is just minimize, it's a regularization term, which is the difference between your parameters and what they were. So if your parameters move a lot very quickly, then that will be highly regularized. If they're not moving too quickly, then that works. So just averaging things out a little bit, putting some restrictions on how quickly things update can actually make a big change in whether your GAN works and starts outputting data like you want, or if it starts failing and either doing junk or just outputting the number 3, something like that. Another idea that they put forward is called one-sided label smoothing. Um, yes, Atom. I love using Atom in GANs, and I think originally a lot of people do tend to have problems with switching on optimizers, and you just have to be very careful with learning rates and momentum and all of those things. So Atom can work very, very well, but if one train's too fast, one train's too slow, you're going to end up into issues, and especially with momentum can sometimes make those issues worse, because if you're going in one direction and then your discriminator changes, so you actually should be going a different direction. It's kind of like online learning. So like Atom works really, 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 really well when you're just trying to get to a point, but if that point moves, then the momentum can mess you up slightly. So Atom, better optimizers do work really well for GANs. You just have to be more careful with what your momentum and the actual options are. So can help you, can hurt you. If you do it right, you're going to end up with faster training because that's what momentum optimizers do. But if you do it wrong, you have too much momentum, it'll just contribute to the same issues as before of overtraining or undertraining, whatever, and getting stuck. So one-sided label smoothing is another idea which can try to smooth out the networks and make them work better. So what this the problem that this addresses is the overtraining. So your discriminator is trying to label 1 for real and 0 for fake. And if it trains 0 and 1, then and your goal is 0 and 1, and you're doing that using sigmoid on your outputs, which goes from not quite 0 to not quite 1, then your network is always going to be training, and your network is going to be increasing and increasing and increasing the weights to try to get them closer and closer to 1, and they'll never quite get to 1, and your discriminator can do this overtraining, which means it's almost fully saturated, and if it's almost fully saturated, it also can't update more, which goes a little bit into Bixhel's question. So if you completely overtrain, then suddenly your discriminator has got parameters in it which are 10 million, because there's never a number which is going to get it quite to 1. And then if things move, then your parameters are these huge numbers and they have to come back down. They need to turn to something else. So if you overtrain, suddenly your network parameters, all the weights are these giant numbers going in one direction, and then when you move and you got to put them the other direction, it's going to take 1,000 iterations for them to become negative again. So this one-sided label smoothing is the idea of not doing hard 0-1 labels. If you label something as like 95, then your discriminator can get there eventually, and it won't keep training, keep training, keep training, keep training. This is actually an important technique in a lot of machine learning. You should try label smoothing on really all of your classifiers. At least give it a shot, see what it does. It's a great general technique, and it's especially helpful with GANs. But I would file that away for your general regularization and machine learning tips and tricks. So really, with any network you're doing as a classifier, if the labels you're giving it are actually 0 or actually 1, then your classifier can overtrain. But if your labels are 0.01 and 0.999, then that's something that your sigmoid can actually accomplish, and you might actually have an endpoint that it gets to instead of just training forever and ever. So experimentally, smoothing works really well, and it makes your GAN smoother, it smooths out your discriminator, and smoothing out your discriminator means your generator can train better. Another idea is virtual batch normalization. I'm not going to dig too much into this, but basically, batch normalization is helpful, just like in everything else. But batch normalization can kind of bring things back to center, prevent too many of the oscillations, and of course, it makes things converge faster and better. So it's a little tricky to do in an adversarial setting, but if you do your batch normalization on your generator and on your discriminator, that will help things out. This technique's a bit of a tangent, but least squares GAN were another idea, which is trying to minimize this loss, which is, let's see if I remember correctly. Yeah, instead of trying to label as 0 and 1 using cross entropy loss, it's trying to label 0 and 1 using an L2 loss. So that makes it a little bit smoother. You take out the log term, and your losses are in a smaller range. So the L2 losses on values between 0 and 1, your loss is going to be between 0 and 1. If you're doing binary cross entropy loss, then your loss is going to be between 0 and infinity. And clearly that's a wider range, causes a lot more oscillations, and using something like an L2 loss can simplify things and prevent the oscillations that we see in regular GANs. Amortized map inference. Oh, right. Very simple techniques, but actually make a big difference with your GAN. If you are doing some noise before you train your discriminator, then your discriminator is going to learn a smoother function and it's going to work better. So what this is trying to say is really all the techniques for smoothing that you have learned, if you start putting them in your discriminator, that's going to affect whether your generator is working or not. In this paper, they added noise, but really everything that you put into discriminators, from batch norm to adding some noise to adding some weight regularization to pick whatever regularization technique you're going to learn about or might come out next year, those techniques are all helpful in GANs and maybe even more helpful than they are in regular models, because smoothing things out means that you actually get an answer. And if things are not smooth, you might just oscillate forever and never get anything that looks like an image. So further trying to simplify things, and this is kind of somewhat building off of the least squares GAN, but energy-based generative adversarial network came out. This is getting us into 2016. So these are a bunch of techniques I've done, I think, mostly just to point out the historical side. Numerics of GANs was 2017, 2017, 2016. The original paper is 2014. So in just a couple years, there are so many ideas that people have been putting out. I think it was about 2018 when the real good ideas started coming out. But so the energy-based adversarial network, this is removing the log losses that are in the original formulation and just doing some very short, just the loss function is just linear, basically. So it's a linear loss function. Your discriminator should be a big number for real, and it should be a small number for fake. Instead of optimizing the log of the discriminator output and 1 minus the log of the discriminator output, you're trying to optimize the discriminator output and the negative discriminator output. They don't squash as much, they don't explode as much. We're just linearizing what we're doing. So that means I can no longer say this is Jensen-Shannon divergence, and I can no longer write out the proof for why it works, but it actually works better than the original. No great theoretical justification, but basically removing the logs made things a lot better. And that was kind of an earlier idea, but what that actually built into is the Wasserstein GAN. So there are a bunch of ideas that people have been throwing together in the 2016 range. And that brings us to the Wasserstein GAN, which was probably the biggest leap. Even though this paper didn't really work that well, it set the foundation for what everyone's kind of doing with GANs these days. So Wasserstein GAN is simplified, it's theoretically grounded, and it works. Yeah, at least this implementation does, and there are a couple papers right after it that work much better. What we do for Wasserstein GAN is we're going to constrain the Lipschitz of the discriminator to 1. That's basically like the upper bound of your gradient of your discriminator is 1. So your discriminator can do whatever it wants, but your discriminator has an upper bound to how sharp it can be. That means your discriminator can never overtrain, never. Your discriminator has got an upper limit to how hard of its slope it can be, and once it hits that slope, the Lipschitz is 1, and you can't do anything. So our loss has become completely simplified. We look at this loss here. The loss function is the first term here, expectation x, meaning draw data from the real world and put it into your discriminator. So the loss is real data going into discriminator minus EZ, Z being your latent data. So generated data, so Z goes into your generator, and then that thing goes into your discriminator. So your discriminator looks at real data, it looks at fake data, and your loss is the expectation over real data minus the expectation over fake data. And we can compare that to all the way back at the beginning. Hopefully I've got the... I might not actually have the original GAN loss in this version of the document. But if you were to scroll back to... Nope. If we were to look at the last slides, you would see that it is... I might not have it in here. But what we have in the original would be EX log of DX plus EX log of 1 minus DGZ. So similar equation if you hold them back and if you hold them next to each other, but we remove the log terms, and suddenly our losses are not going between 0 and infinity, they're going between 20 and 30, whatever it is. And with the linearization, things tend to be less unstable and ramp up and ramp down in a different way. As you can imagine, if your loss has got a log in it, then going from 0.1 to 0.01 is a really, really small change, and that's 10 times whatever it is. So things can escalate and de-escalate very quickly versus with a simple linear model. So what is this actually doing? And why is it called the Wasserstein GAN? And that's because of the Wasserstein distance. So Wasserstein is a distance measure. It is a true distance. If you guys are taking more stat, you'll understand the difference between a distance and a divergence, but it satisfies all of your triangle issues. It satisfies triangle inequality. It is symmetric, so it has all the it is a full distance. It's not a divergence like KL, for example. It is very hard to calculate, but what the Wasserstein distance basically is how far something would have to move to become something else. It can be called the earth mover metric because it's like if you had a pile of sand over here and you wanted to make it into a different pile of sand, how many things would you have to move how far? So to convert A into B, I need to move 3 pounds of sand, a total of 5 feet. The Wasserstein distance would be 15 pound feet, whatever. Not that we have units in what we're dealing with most of the time, but just to give it a hard example. So it's the idea of a transport plan. It's move things from here to there, and solving for the Wasserstein distance itself is NP hard. So Wasserstein's distance is much better, but figuring it out is harder. Just for a visualization, the Wasserstein distance, let's say A is my red points and B is my blue points. The Wasserstein distance between red and blue would be the total sum of how far each red point needs to move to get to not the closest one, but get to the one where it needs to line up. So if all of the red points were on top of all the blue points and the distributions were exactly the same, how far would you have to have moved each of the red points? And that is your Wasserstein distance. And the Wasserstein distance is much, much better than KL in a lot of situations. And to explain that, here's the example. So your KL divergence is P log P over Q. You've probably seen that a bunch of times, and if not, you will see it a lot more before you're done with CMU. But P log P over Q is your KL divergence. And let's say we've got 2-point masses. And your real data is a point mass at 0. Your generated data is a point mass at 1. What would that mean? Well, the KL divergence is infinite. If you've got 2-point masses and those point masses are not directly lined up, then the KL is infinite. Because this KL divergence, as it's written, you see it's an integral over x. And that means at each x, it's completely independent. So if my data, I'm outputting data that is 0.1, and you're outputting data that is 0.2, well, the likelihood of me outputting 0.2 is 0, and the likelihood of you outputting 0.1 is 0. So that means our log term is going to have 1 over zeros in it, and it's going to have zeros over ones in it. And that means your KLs will be zeros and they'll be infinites if things are not equal. I'm sorry, not 0. But it'll be here we go. It'll be 0 only when the 2 points match exactly, but when they're different, then it goes to infinite. Jensen's-Shannon divergence, very similar issue. So if you've got 2-point masses and they're not the same, then the Jensen-Shannon divergence is log 4. And it doesn't matter if the real data is at 0.1 and the fake data is at 0.2, then the divergence between those two distributions is log 4. If the real data is at 0 and the fake data is at 10,000, then the divergence between those two distributions is log 4. So Jensen-Shannon and KL divergence are actually not that helpful for certain types of distributions. They're just not good metrics that don't really mean anything. And the reason they don't mean anything is they just tell you if two things are the same or not, but that's not a helpful thing to know. You want to know how close something is. Wasserstein distance is the distance that you have to move something for them to be the same. So if I've got real data is at 0 and my fake data is at theta, then the earth mover distance is the absolute value of theta. So if my real data is at 1 and I want it to be at 0, the earth mover distance is 1 because I need to move it 1. If my real data is at 0 and my fake data is at 10,000, then the earth mover distance is 10,000 because I need to move it 10,000 to get back. And what that means is the earth mover distance has this nice slope to it. The earth mover distance gets lower when things become closer to each other, versus KL and Jensen-Shannon divergence basically are the same until two things are the same and then they're zero. Just graphically speaking, on the left, here is the Earth mover distance as you were to move around zero. So I want to be at zero. If I was at -1, my Earth mover distance would be 1. If I was at 1, my Earth mover distance would be 1. If I'm at 0.5, my Earth mover distance is 0.5 because I need to move 0.5 to be back at 0. Compare that to Jensen-Shannon divergence. The Jensen-Shannon divergence is the same value no matter where I am, unless I exactly equal where I want to be, and then it's at 0, and then it goes back to what it was before. So Jensen-Shannon divergence, this picture on the right, is actually what the original GAN formulation is trying to optimize. And you should be able to tell from this picture, if I was trying to optimize this thing on the right, I would not get to that 0 point. Because there's only one point that works, and it's not like anything around it is pointing to that direction. There's no nice slope going to that point 1, to that 0. If you were to modify the thing on the left, if you were optimizing this point on the left, you would get to that 0 every time, because there's a nice smooth line, there are no jumps, no edges, no discontinuities or anything. Just optimize the EM and you should be where you want to be. If you try to optimize the JS or the KL, then you're going to get these discontinuities, and that doesn't help you tell which way to go. The reason this works, it's actually called the Kantorovich dual, which is a dual solution to optimal transport. So optimal transport is this idea of, let's move each red to the blue point that it should go to. And that's actually an NP hard thing to do, because maybe this one's closer to this one, but it should really go over there because that's where things need to move. And figuring out what the shortest route for each thing to move to become something else is kind of like traveling salesman or anything else. It involves a lot of different possibilities, and it's hard to figure out what the right choice is. However, we can do this calculation of the dual, and this is coming from optimal transport theory. This is coming from your math classes, but this solution to the dual formulation of optimal transport and the Wasserstein distance actually explains why GANs work and how they work. So, sorry, just 1 second. Just to make sure everyone understands this. Don't worry too much about what this is saying in terms of optimal transport theory and the kind of idioms that they use. But basically, there's a transport plan, and you're trying to optimize a transport plan where you can move things and they're the same. So
What is
what
C
is
over here?
I'm sorry?
What is CXY?
CXY. I believe CXY is how, I want to say the mass. I could be wrong about that. Yeah, it's like how much you move from here. I have to look up the actual details because this slide's been a while. But let me see if I can remember. I want to say psi is your plan, and phi, or maybe it's the other way. Honestly, I'd have to go back and remember what each of these are. But the yeah, no, yeah, that's right. It's the mass at x and the mass at y, and then I think how far they are apart. And I actually have to select that side. But in terms of what it's doing, if you're calculating the supreme, that's right. That was the no, actually no, that wasn't the Lipschitz. I'll have to go back and see if I can remember those. But anyways, what we end up doing with this WGAN and why the WGAN is better than your regular GAN is if your regular GAN, let's say I've got real data over here on the left and I've got fake data over here on the right. If I train a 0-1 sigmoid GAN to separate the two of them, this is kind of the line that it will draw. And you see that line is like very flat and then vertical and then flat. And yeah, you can optimize that, but it's hard to do. And the harder this discriminator gets and the more vertical it gets and the more horizontal over here, the harder it is for you to learn which way to go. Your WGAN, instead of being 0 to 1 and squashing at 0 and 1, is clipped at this, like, it can only be a Lipschitz of 1. That doesn't quite look like a Lipschitz of 1 in this situation, but you're you're setting an upper limit to how sharp the WGAN can be, and because there's a limit to how sharp it can be, it's nice and smooth, and you can actually go down that way or go up that way. So WGAN doesn't go as sharp. By definition, WGAN has a Lipschitz upper limit, so you're not going to end up with these vertical lines, and then the vertical lines kind of cause these horizontal lines next to them where you really don't have information. Yeah, it's kind of hard to see the points. If that's 0.5 to, is that 1 to 1? Yeah. I'm going to trust them that this is a Lipschitz of 1, but if you actually check I'm trying to see what that slope actually is on the scale, and the vertical scale is kind of weird, but the idea stands. So anyways, what's the catch here? The idea is if you can constrain the Lipschitz, then you can calculate the Earth mover distance. And if you can minimize the Earth mover distance, then you go where you want to be and everything should work perfectly. So what's the problem here? The problem is, how do you constrain the Lipschitz of a function? I've got a neural network. The neural network has millions of parameters, and I want to declare that the Lipschitz does not go above X. And that itself is hard to do. So we've taken a hard problem, converted it into another hard problem, converted it to another hard problem. So our GAN problem now that we've reduced it to, mathematician's answer, we've just reduced this to the problem of constraining the Lipschitz of a function, which is itself really hard, but we might have ways to do that that are easier than things we were trying to do before. So we can't ensure the Lipschitz, we can't guarantee it and make that the only thing that we're guaranteeing for a neural network. So the Lipschitz is, dx minus dy over x minus y. This is squared because that's the L2 Lipschitz, but, any Lipschitz is fine. But if you wanted to calculate that, you would have to do that for every single point in the data. So the way that they constrained the Lipschitz in the first paper, in the WGAN paper, is to clip the weights. So if we were to clip the weights of every single weight in your network, then I could guarantee that the Lipschitz does not go above a given value. It might not be 1. I can tell you what that number is based on what we clip it to. But if we're clipping the values, then we have an upper bound to our Lipschitz. The problem is that upper bounding the Lipschitz by clipping every single individual weight to just a number doesn't give you a very tight bound of the Lipschitz. It gives you a lot of artifacting, and the actual results are not great. So the Wasserstein GAN paper gives us great ideas about what we want to do, but the actual problem of how do you constrain the Lipschitz, it did not solve very well. So the kind of updated paper, this is one I would actually recommend implementing. It seems to work really well. It's been very reliable when you're doing your training. And this is the Wasserstein GAN gradient penalty. So that is opposed to the other one when we just saw, which is weight clipping. So weight clipping didn't work too well, but the gradient penalty seems effective. The idea is the Lipschitz should be 1 everywhere. So let's just sample the Lipschitz and add a regularization term that it should be close to 1. So if you look at this loss function at the bottom, you'll see this first part here. That is the Wasserstein GAN loss. That's going to be similar to your original GAN and just pulling out the log term. So there's no more log in there. It's just the expectation of X of the real data and the expectation under the fake data. One's positive, one's negative. So you want to optimize one or maximize one, minimize the other. What we add to this is a regularization term. And this is the new part in Wasserstein GAN gradient penalty. And what that term does is, what is the gradient of the discriminator? -1 squared. So you should look at these two terms as just like an L2 loss, meaning if dx squared is different than 1, then this term will increase, and this term would be equal to 0 if the gradient of the discriminator is 1 at all points. So that's exactly what we want. The problem is we're just doing an expectation. So I can't tell you for sure the Lipschitz is 1 in this function, but I can sample the function at different points, and I can regularize for any time that it's not 1, and that can get the gradient near 1 at most places. And that's practically speaking good enough for a GAN. And the trick here is, where do you want to sample? So I need to sample random points, and at those random points, I want the Lipschitz to be about 1. So what I do is you randomly pick points by interpolating between real and fake data. So I don't care if the Lipschitz is not 1 everywhere in the world if I'm not using that part of my network. It's a region of the space no one ever gets to. The important thing is I'm going to sample a bunch of points that are in between my real and my fake data, sample a bunch of points in that region, and make sure that the Lipschitz is about 1 in the region between my real and my fake data. And as long as that's happening, then I'm correctly calculating then my Lipschitz is upper bounded, and my Lipschitz is upper bounded. Then I'm calculating my Wasserstein distance. And if I'm calculating my Wasserstein distance and minimizing it, then two things match, and that's what I want. What we've got, so kind of visualizing what happens. The top row is what happens with the original Wasserstein GAN paper, which used weight clipping. If you do weight clipping, you basically end up with these very boxy lines. If you train a discriminator on it, it kind of gets the point, but it's not able to quite fit the shapes because of the weight clipping. Versus the second row is using the WGAN GP critic. And we see that when we train that, we've got really nice orderly lines, which seem to match up to drawing circles around where you want it to be. So real data, yeah. So the clipping was a beautiful paper that made great steps, but the implementation did not do anything meaningful at all because it made things really boxy. But the Wasserstein GAN gradient penalty paper gives you nice, smooth discriminators that don't oversaturate or anything, and do a pretty good job of getting you to where you want it to be. Another interesting idea for how to optimize the Lipschitz, or how to constrain the Lipschitz, is the spectrally normalized GAN. This is another one that I would recommend, kind of either this or the Wasserstein GAN gradient penalty. What the spectrally normalized GAN does is this is using basically just linear algebra to calculate a bound on what the Lipschitz is, but it's an okay bound. It's not great, but it seems to work pretty well in process. The way the bound is calculated is you can use linear algebra to tell you what is the Lipschitz of a matrix. That's very straightforward. You can tell it's just what's the largest eigenvalue of this thing. And that tells you how much the matrix can blow up your stuff. And if we think of our neural network as a stack of matrices, then if my first layer has a Lipschitz of 2 and my second layer has a Lipschitz of 4, then that means my overall network has an upper bound of a Lipschitz of 8. That doesn't mean that is the Lipschitz of your network, but that means I can put a bound on, I know your network definitely doesn't have a higher Lipschitz than this. Because if your first layer multiplies by 2 and your second layer multiplies by 3, then overall, there's no way these two things together do anything more than multiplying by 6. Might be less, but I've got an upper bound. So you can calculate the Lipschitz of each matrix. That is the spectral norm, basically. So the spectral norm of each matrix in each of your layers, and then product of all of those is the total upper bound of the Lipschitz of your entire network. And if you then just divide the network by that value, then you know the network has a Lipschitz of 1. So basically, if you give me a neural network and you tell me the Lipschitz is 5, I can say, okay, great. That network divided by 5 has a Lipschitz of 1. And that way we are constraining the Lipschitz. This does not involve sampling, it involves a bound. And as I mentioned when I was first talking about VAEs versus GANs and kind of a trade-off you'll see frequently in just machine learning in general, there's something really complicated. So ideally they would all be equal to 1, almost everywhere. Almost everywhere is a term we use to mean basically everything but specific discontinuities and points. So if you were actually solving the true optimal transport problem, and this was, yes, this definitely is the function that is the optimum, then the gradient would be 1 every single point, and then there'd be some saddle points, or not saddle points. There'd be different like minima and maxima where the gradient would be, 0/undefined, whatever, there'd be discontinuities, but you would expect 1 at every single point. Since we're doing sampling, if we're saying 1 almost everywhere meaning everything but discontinuities, then basically the same. Practically speaking, it should be limited to 1, but the reason why smaller and close to is also kind of going back to what I was saying about sampling versus bounding. So when we're doing sampling, we're saying everything should try to be 1. And I'm getting a bunch of samples from all over the data set. Some might be 1.1, might be whatever, but I'm going to try to get them all as close to 1 as possible. And I can't guarantee that everything is less than 1. I can't force everything to be less than 1 because I'm just sampling. And maybe everything I've sampled so far is less than 1, but I sampled something else and it's a 2. So because we're doing sampling, we're trying to get close to where we want it to be. Versus when we're doing a bound, like spectrally normalized GAN, I can guarantee you, like 100%, that your neural network does not have a Lipschitz above 1. But maybe your Lipschitz is like 0.1. I don't know. You might not be getting close to the bound. And that's the trade-off you see a lot. Yeah, it's the singular values are below 1, or you could look at it as the total singular value is below 1. And you know that you're going to meet that Lipschitz. You know that your Lipschitz is below 1, but you don't know how far below 1 it might be. It's a bound. Bounds, some of them are tight, some of them aren't very tight. Most of them aren't very tight. This is one of the not very tight ones. So you might be losing out. Versus if you were to do the sampling method of the Wasserstein GAN GP, if you were to have infinite samples, then you would really truly be solving the exact thing that we want to solve. It would just take infinite samples to do it. Versus when you're doing a bounding, I don't need samples. I've got the data. I can calculate it. I can just do it right here. But that may be way off. It may never be close to what I actually want to be. So, in terms of which one's better or worse, spectral normalization is kind of guaranteed, and you're not going to have to do a bunch of sampling or anything. So you can guarantee you're getting that Lipschitz to be constrained. But because it's a bound, you still see some artifacts. You're not going to see as many artifacts as the first paper, which had a very bad bound. This is a better bound than the first paper, but it's not. No bound is perfect. And you're always stuck with either bound and hoping it's close enough, or sampling and hoping you've sampled enough, and kind of the way the two play off each other. Those are your choices. So I'll briefly mention Fisher GAN, which is also a constraint, also not using sampling. It constrains the difference between the two of them in a way, but the problem with Fisher GAN is not quite smoothing the region in between. So if you got generated data on one side and real data on the other side, the Fisher GAN sets a bound to how different the two can be, but it doesn't necessarily smooth out the region in between. And the key point to both the spectral normalized GAN and the Wasserstein GAN GP is the Lipschitz is being limited at everywhere that matters, at least everywhere between real and fake data. So it's not just that the Lipschitz is, or not the Lipschitz would be 1 point. It's not that the gradient is 1 at this point and at that point. It's that in between all of these points, the gradient is also 1. So that means that you smoothed out everything. These are a couple other brief mentions of Laplacian GAN. Is an idea to try to do smaller images, do progressive, and try to split up your GANs. That actually helps a lot in terms of stabilization. And progressive growing, which is trying to use gradually larger and larger and larger discriminators, adding layers, expanding your network so that you're not trying to learn all at once. And progressive GAN, this is kind of a picture of what they do, but they start adding more and more layers to make things sharper and sharper, and to make your discriminator sharper and sharper. And at the end, they've got a really sharp, good-looking image that might not have converged if you just tried to do it all at once. And yeah, so the takeaways from this idea, if I give you an NP problem, you can make that into another NP problem, and that's basically the best you can do. And if you can do better than that, then please let me know. But there are many ways to try to make it a little bit easier, a little bit more approachable. Still NP, but we've got little hacks and little things that make it a little bit better. So unrolling, there are some computationally expensive methods. There are sampling-based methods. The sampling-based methods are as reliable as your sampling is and how much sampling you have. And bound-based methods can have artifacting. And those are kind of your two choices of samples or bounds for trying to clear up the data. So the original WGAN and the spectral normalized GAN are examples of bounding. So pretty easy to calculate, run pretty quickly and reliably, but you will get artifacts pretty much guaranteed. And the sampling methods like WGAN GP, where run a lot of samples, but your potential for actually getting to where you want to be is pretty high. And some major ideas in the research. I showed you a lot of different ways of. Oh shoot, am I over time? It's 9:30. Pictures on mute, but I guess I gotta wrap up.
Okay, so you have a couple of minutes, and I've got to stop.
Yeah, besides, but major ideas are cleaning up the discriminator, simplifying the discriminator, smoothing it out, constraining it. Many different things that have been thrown out, just trying to make this train better. And very impressive results, but a lot of GPUs, a lot of research. Results are getting better. People are using it on new things like audio and text and everything every day. Most of the research has been on images, but you guys are got plenty of work ahead of you, whatever you want to use it on. And hopefully it's going the right way, which is we've got a meaningful assessment of whether two things are different. Not L1, not L2. We can look at perceptual distance between things, make things match. We can measure these things, and we can actually reproduce things that fool human beings. And that's our goal here. So have fun with GANs. Definitely try WGAN GP if you need a hand. We should have some implementations out there, hopefully, in recitation notes or something. And good luck with everything, guys. Any questions?
Questions? I think not. So we're about 10 minutes over. So I'm stopping the recording. Thanks a lot, Ben.
Appreciate it, everybody. Take care.
Bye.